Hello, I'm glad that you are joining us. We are having you change how we do things, so we'll be providing online videos for class in replace of lecture. That you will be pausing the video and trying the problem out on your own prior to me doing it. So that way you can see if you got it and then see how we went about it. Also, make sure that you are rewinding and replaying just in case you might have missed something or if you didn't understand something. We will hold virtual meetings. You will be getting more details upcoming if you haven't already got the details already, depending on when you look at this video. Thank you so much for your commitment to being successful in this class, and let's work together to make sure that we complete our class and complete the course and be successful in doing so. So I look forward to working with you as we progress through. I just want to repeat number 86, and just literally I'm just going to write some rules on the right hand side just to remind us of the rules that we already know. We have our product rule that says that might not write all the rule names, but the product rule that says that x to the m times x to the n is equal to x to the m plus n. And I don't know if in class if I used x or if I used a, it's still the same thing as long as the bases are the same. Our quotient rule, we reviewed and we said that x to the m divided by x to the n is equal to x to the m minus n. And remember I said think of it like your fingers, you know, how many are on top, how many are on the bottom, and count them out and see where you are. So you want to count out how many fingers you have on top, how many on bottom, and see which cancels. And that might give you an idea in terms of, instead of having to subtract every time. We looked at the power rule, and remember there are three power rules. One is power over product, power over quotient, and regular power rule. We had x to the m to the n is equal to, and that's an m, x to the m times n. Then we have x to the x over y to the m. This is power over a quotient, and we end up with x to the m over y to the m. And then we had x over x times y to the m, power over product rule, which is x to the m, y to the m. So we went over that. We have those in our arsenal. We also went over what we call our zero exponent rule, and I'm coming over here because I'm running out of room and I don't want to move out of this screen just yet. Our zero exponent rule, where we had anything to the zero power is equal to 1. Technically we write it as x to the 0 is equal to 1, but I like this one because it reminds you that no matter what you raise to a power is 1. Then we have what you call the negative exponent rule. And that says that a to the negative m is equal to 1 over a to the m. And then we had 1 over a to the negative m is equal to a to the m. So these are the exponent rules that we wrote. We also wrote a rule in terms of radicals, in terms of power rule for radicals. We wrote another rule in terms of changing it to a rational exponents and etc. Where we had x to the m over n. You can look at this as x to the 1 over n to the m, or you can look at it as x to the m times 1 over n. Remember that multiplication, when we raise to a power, we multiply. So we're doing m times 1 over n. Well, that's the same as vice versa. So that's called the commutative property. That allows you to change the order of the information. So just reminding you of the information. So then I can rewrite that, and I'm going to have to zoom out because I'm running out of room. I'll just shift it up some and then zoom back in. Excuse me. We're playing with the machine. But what we're doing is we can rewrite this information here as x to the m over n in radical form is equal to, well, the 1 over n, we know that is the nth root of x to the m. Or we can write this as x to the m, where x to the m, not the third, excuse me, and then the nth root of x on the outside. So all I did was rewrite what we wrote here in rational expression form in the radical form. So we looked at this in the radical form. So those are the formulas that we went over on last class before we left school and before we shut down for a week. Let's review number 86. I was told on discussion board, and thank you again for letting me know. I think it was Kaylin who let me know. Thank you so much for letting me know. Ooh, I don't want to violate any verbal rights. Well, I just said your first name. I didn't say your last name, so we're good. So, thank you for letting me know that we discussed this online, that we left off on 86. But I just want to repeat it to make sure we get back on point of where we are. We had 2 to the 5 6 times 2 to the 1/3 over 2 to the 1/2. And we saw that they all have the same base. So we have the product and the quotient rule going on. So this becomes 2 to the 5 6 plus 1/3 minus 1/2. And we went on the side and did our fractions. We found the common denominator. In order to add or subtract fractions, you need a common denominator. Do y'all agree? I do hope so. I hope you remember this. What do you have to do to 3 to make it a 6? You have to multiply by 2. So I'm going to multiply top and bottom by 2. And then times this by 3 to make that a 6. So if we do that, we end up with 2 over 6, and we end up with 3 over 6. 5 plus 2 is 7, minus 3 is 4, so we get 4/6, which is equivalent to 2/3. So this becomes 2 to the 2/3. And I believe that they asked us to leave it in rational form. So they asked us to leave our answers with problem. And so we can get back into the swing of this. Let's try another problem. Let's do number 90. Number 90. What does 90 say? Well, what does 90 say? Well, 90 says y to the 2/5 times y to the negative 2/5, y to the 3/5. So here we have something on the outside multiplied by a binomial on the inside. Well, really just multiplied by a two-term expression. We should be able to distribute. Do we agree? So I'm going to be distributing both of these here. And remember, you got to multiply both, not just one. But when we distribute, we're multiplying, and they have the same base, so what can we do? The product rule that we saw here says if I multiply with the same base, I can just add the exponents. So just as a reminder, we're going to add the exponents. 2/5 plus a negative 2/5 is just 0, so that becomes y to the 0, plus 2/5 plus 3/5 is y to the 5 over 5, which we know that's y to the 1. So I end up with y to the 0 is just 1 plus y. And I really feel like we did this problem, but we might not have. But I feel like we did. Maybe I'm remembering last semester. I don't know. Let's try another one. And I hope you got that. And rewind it if you need to make sure that you understand it and make sure you didn't miss a point. Let's go with 98. It says the 8th root of q squared. 8th root of q squared. And it asks us, yeah, I did this problem. I remember doing it. It asks us to use rational exponents to simplify each radical. So we're going to use the rational exponent to simplify the radical. So how can I rewrite this? Well, I can rewrite this in rational exponent. The inside is your numerator. And the index is your denominator. So remember that when you write this in rational form, your index is your denominator. So we end up with q squared, q actually to the 2/8. And if we reduce that, we end up with q to the 1/4. And then we're going to change it back to radical form. So we're going to end up with, well, the index now is the 4th root of q. So notice that our radical is able to simplify down to the 4th root of q. And again, hopefully you paused it before we tried it and can go from there. I'm going to go to number 104 now, and that's on the subsequent page. So that's on the next page, 104. We're looking at the cube root of the 4th root of 21x. So we got the cube root of the 4th root of 21x. And maybe not right now, you would want to try to do this. Try to do this on your own. See if you can figure it out. But let's do this together. I'm going to do it, but hopefully you'll push pause and try it on your own. Again, you cannot just learn by watching the video. You actually have to try it on your own. So we start off with the 21x. And we write this in rational form for the exponent. We get 1/4. Then it's raised to the 1/3. Well, what do we do with powers when we raise to another power? Well, we'll see that in the power rule that we wrote above. We found out that if we raise a power to another power, we multiply them. So if I raise a power to another power, I multiply them, then I end up with 21x to the 1/4 times 1/3. Isn't that 1/12? And then I rewrite it as a radical. Now my index is 12, and we have 21x to the first power, which is just 21x. And that simplifies my radical. We are done with 9.2 now, so we're going to move on to 9.3. We are done with 9.2, so we're going to move on to 9.3. I'm going to zoom out a little bit because I think I've zoomed in a little bit too much and see if that might help. Let's go 9.3. 9.3 is simplifying and combining radical expressions. And again, if you can't read my writing, you might just want to rewind and replay because you know I tend to say what I write. So rewind, replay, so that way you know I tend to say what I write. For the page, in terms of what page we'll be on page 762. So we're going to be on page 762 in terms of our examples. They'll be on page 762. So let's go to work with this. Here we go. When we talk about simplifying and combining radical expressions, we want to start off talking about, for some reason I feel like I've done this video already. I did 9.3, I did the quotient rule. No, we didn't do it. Okay, so I started it and then I stopped. Okay, that's what happened. All right, so I felt like I did this already, and I probably did, but I didn't. I stopped it in the middle, so I didn't count it. I tossed it and I tore it up. So let's get started back into it. I want to start off by saying let the square root of a and the square root of b be any real number. So I'm going to start off by saying let square root of a and square root of b be any real number. Of course, you know the square root of a is our principal square root, so it's positive, and our square root of b is a principal square root, so it's positive. Then, that implies for the product rule. Product rule says that the square root of a times the square root of b is equal to the square root of a times b, and also vice versa. So you can look at it that way and vice versa. Please note something. Side note. The square root of a plus the square root of b is not square root of a plus b. That is voodoo. That is not true. The square root of a plus the square root of b does not equal the square root of a plus b. Again, that is voodoo algebra. So do not try that in terms of your problem, because I will tell you, voodoo algebra. So let's not do that. So we have, you can multiply under the radical, but you cannot add or subtract and combine them under the radical. It only works for multiplication. Let's do the quotient rule while we're at it. You might as well kill two birds with one stone. Let's do the quotient rule. And it works just the same way. The square root of a over the square root of b is equal to the square root of a over b. So the entire square root. So that entire radical is equal to the square root of ab. Now, keep in mind that this just not only works with square roots, but actually technically this works with the nth root. So we can do this with more than just any square root. But we have to be careful with our negative signs when we deal with radicals. But this works for all square roots. All right, so here we go, the quotient rule. And then this is also vice versa. Before we actually do the math and actually talk about simplifying and getting into it, I want to talk about the simplified form of a radical. So we're going to talk about the simplified form. Now I want to try something. I want to see if using a pencil would be just as effective as using a pen, because you know me, I make mistakes all the time. The simplified form of a radical. Let's see if you can read it just as well. Yeah, almost. It says each factor. Each factor. Oh, I know what I did this for. I typed the notes out. I see what I did this for. And you will have this in your notes, and it'll be written in much more detail. Each factor's power. Each factor's power has to be less than the index. So any variable underneath or any number, the power has to be less than index. If you have a square root and you end up with a number under there that's 8, you know that 8 is 2 to the third. That power is not less than the index. If I end up with the square root of 8, we find that we end up with the square root of 2 to the third. This power is not less than the index, which would be a 2 there, so it's not simplified. So keep in mind what we mean by simplified. It's not simplified. Number 2, the radicand has no fractions. Doesn't have any fractions. And of course, I know how to use English, but we're doing the abbreviated version online. Here we go. The radicand does not have any fractions or negative numbers. So there aren't any radicals in the denominator of a fraction. And in the next section oh, there we go, it unfroze. Do I like the black better, or do I like the pencil better? It's almost 6 eggs in one hand, half a dozen in the other. The black one is a little bit more potent and is a little bit more bold, and you can see it better. I don't know. We'll try it. Let's see. I think I'll go back to the pen because I think I'm a little bit more comfortable with that better. And then in terms of you being able to view it, that's what I'm concerned about, is you being able to view it no matter what whatever you're using. Let's try some examples. Let's do number 14. I want you to be able to view it. I want to make sure that you can view it. Remember, again, I told you we're on page 762. So I want to make sure you can view it. Let's do number 14. Number 14 says, what does 14 say? 14 says square root of 28. So we want to do the square root of 28. And my screen blanked out, and I do apologize, but that's because computers time out after a while. Square root of 28. When I see square root of 28, we want to write this in simplified form. To do these problems, it's a good job to list out all your squares. So let's list our squares, and we did this before, but let's do this again. Let's list out our squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is, I think we ended up with 196. 15 squared, and again, like I did when I videotaped my other class, I didn't bring a calculator. 15 squared is 225. Let's go with 25 squared, which is my favorite one, which is 625. So if we have a list of squares, so I want to be able to use the product rule here to simplify this expression. So I want to be able to use the product rule. Remember that the product rule says that if the square root of a times the square root of b is equal to the square root of a times b, and vice versa, the square root of a times b is equal to the square root of a times square root of b. If I look at the right side of my squares, so the values that we do after we square them, is there a number in the right side that will go into 28? Yes, 4. 4 can go into 28. So I can rewrite this as the square root of that 4 times 7. Well, remember we said that we can also break it up. So we can break it up knowing that square root of a times square root of b is equal to square times a times b. By that product rule, then this is equal to the square root of 4 times the square root of 7. But what's the square root of 4? Isn't the square root of 4 2? So that gives us 2 square roots of 7. So what you want to do is you want to take out that perfect square. You want to simplify that perfect square out of the radical with the quotient rule. All right, let's do it with variables this time. Moving on, let's try another problem, and hopefully you're pausing it as we go to try it before we try it, so that way you can make sure you understand it. Let's do number 24. Number 24, what does 24 say? What does 24 say? It says the square root of 75, b to the 8th, c. So I want the square root of 75, b to the 8th, c. So I'm going to show you this the long way first, and then we'll do the shortcut later. Yes? We'll do the long way first, and then the shortcut later. So I look at 75. Looking at that list of perfect squares that we just wrote, is there a perfect square that can go into 75? Yes, 75 can be written as 25 times 3. Oh dear. Times 3. Then we have b to the 8th and then c. Well, we can separate all these radicals into individual radicals, and that is square root of 25 times square root of 3 times square root of b to the 8th times square root of c. Some of them we really don't have to break up, but we're doing the long way first and then the short way second. So we're going to do the long way. You know how I am. I'm going to do the long way first, and then we're going to simplify it second. Well, I know the square root of 25 is 5. And I know the square root of b to the 8th is b to the 4th. So we end up with 5b to the 4th on the outside. And what's left over is the square root of 3 and square root of c, which we combine to just write 3c. And there we have this problem. I'm going to do it again, but I'm going to shortcut it this time to try to make it a little bit more feasible in writing, because how many people want to write all that? I don't either. So what is the index out here? The index out here is a 2. Do we agree? Okay. So first we start off with our numbers. Just to put that in. Just to plug that in. Put a pin in that. 75 is 25 times 3. Do we agree? Square root of 25 is 5. So we pull the 5 out. Now we move over to our letter. 2 goes into 8 how many times? 4. That is b to the 4th. Miss B, why can you do that? Remember, if I wrote this as rational, wouldn't this be the square root of b to the 8th be the same as b to the 8th divided by 2? Remember the rational exponents we did? So instead of writing it out this way, I can just do long division. 2 goes into 8 4 times. And that just simplifies it. What's left over? Well, what's left over is this 3 on the inside and the c that's left on the inside that we didn't touch. So we touched these two. And that's what we have in the front here. So I can color code it and let you know where they come from. That's just a shortcut way that I like to do it. I like to write things a little different. You can always write it the long way. Again, you can write it the long way, but I'm a shortcut person, so I like to write it a little bit more abbreviated. Let's try another one. Let's do number 36. And hopefully you're pausing and trying the problems out before you watch me do it. You try it first, and then if it doesn't work, then we go there. Before we do 36, we need to list out the cubes. We did the squares first. Now we need to list out the cubes. Let's go. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed, I'm getting nervous because I'm on the internet and I'm putting myself on YouTube, so that causes a little bit of nervousness, but it's okay. We can handle it. 6 cubed is 216. 7 cubed is 343. Uh-oh, got the 8 cubed and I done forgot. I think it's 512. But I want to make sure. 32, yep, 512. 8 cubed is 512. 9 cubed is 728. 81, 729. 10 cubed, well, we know that one, that's 1,000. Oh, I didn't leave myself enough room. Let's keep writing. 11 cubed, that's 1331. 12 cubed is, I believe, 1478. I'm trying to look and find my cell phone real quick, so that way we can calculate this real quick, because you know, my smart self forgot her calculator. She didn't bring her calculator with her today. I was really smart. I had a moment today. And I'm using the app that we talked about in class that I have on my phone. I'm using the app that we talked about in class that I have on my phone. This Wabbit EMU. It's on for Google Play, and then iPhone has a form for TI-84 for calculators. So I have TI-84 for your cell phone on here. So let's do 12 to the 3rd power. And we end up with 1728. Oh, I was off a little bit. It was 1728, not 1428. Oh, my dear. Made a mistake. All right. Let's go with 13 cubed. It's 2197. Really, we can stop at 12. Usually we stop at 12. We really don't have to go beyond that. So I think we'll just stop at 12. We went on to put 13. Well, I might as well put 14 and 15 on there since we're going. And I'm going to stop at 15. So that's what we have in terms of cubes. So this time, instead of thinking about what becomes a square, we're still going to be looking at the values on the right hand side to help us figure out how we can simplify that cube root. So we have the cube root of 280, a to the 5th, b to the 6th. Is there a number on the right hand side that goes into 280 evenly? Well, you know 216 is not it, and 125 is not it. You know that off the top, because 25 doesn't go into 280. So you know that's not going to work. So then I'm going to move up. I'm going to see if 280 is divisible by 64. Nope. So then I'm going to move to, I know 27 is not going to work, so that means 8 should work. Let's try 280 divided by 8. And yep, it does work. So 280 divided by 8, and I'm going to approach this the same way we did it before. I'm going to break this down to 280, breaks down to 8 times 35, and 8 is what I can simplify. So when I do that, I end up with the 8 on the outside, and then I have a leftover on the inside, the 35. So I can take that 8 out. I can simplify that 8 factor of 8 out, because the cube root of 8, is not 8. The cube root of 8, is 2. The cube root of 8 is 2. Do not make that mistake that I just made. Cube root of 8 is not 8, it is 2. I hope I left myself enough room. Now remember, I told you the shortcut above. I told you the shortcut we can divide. So 3 goes into 5 how many times? It goes in there once. So I'm left with 1a on the outside. And now how many left over? So 3 goes into 5 one time. Subtract 2, and I have 2 left over, so I have a squared on the inside. And then 3 goes into 6 twice, so we have just b squared on the outside. So my answer is 2ab squared, cube root of 35a squared. And that is exactly how we simplify that problem. And just shortcutting it so you don't have a lot to write. Let's go to number 40. Let's try number 40. Number 40 is the 5th root of 2 over 243. So we're going to do 5th root, and this time we're going to be doing quotient rule this time. So it's already together, so I can break that apart. Remember, we wrote the quotient rule earlier and said that the quotient rule, if I get my piece of paper, we wrote it earlier. We said the quotient rule, if I have the square root of a over square root of b, is equal to the radical of a over b. So the same way here, the 5th root, same with 5th root, it's just any root. I should have put an n there for all indexes, but any radical, it works that way. So this really just becomes the 5th root of 2 over the 5th root of 243. I'm not getting ready to list out the powers of 5, so guess what I'm getting ready to do? I'm going to type in my handy-dandy calculator. I know that 243, 5th root, I can rewrite that as 243 to the 1/5 power. When you type it in your calculator, you're going to go 243 caret, parentheses, 1 divided by 5, close parentheses. So let's do that at this time. And some of you have the capability that it just goes up into the power and you don't necessarily have to put the parentheses. But those of you who don't have that capability where it goes into the power, you have to put that parentheses there. You end up with a 3 when you get done. So my answer is the 5th root of 2 divided by 3. And hopefully you paused it and tried it on your own prior to me doing the problem again, just reminding you. Let's do number 44. And hopefully you'll do this, pause it. I'm going to write the problem out and then you will pause it and try it. Let's take the square root of b to the 4th over 64 a to the 8th. Now this section, they work out pretty. Next section, we'll talk about rationalizing the denominator. We'll do that on next section. Not this section, but next section. So again, remember, I can break them up. So let's break them up. I get the square root of b to the 4th over the square root of 64 a to the 8th. When I do that, let's write this out. If I take this, what's the square root of b to the 4th? Well, that's just b squared. What's square root of 64? Well, we know that's 8. And then the square root of a to the 8th is a to the 4th. And guess what? We're done. Remember that number on the outside, our index here is a 2. So 2 goes into 4 twice. 2 goes into 8 4 times. So that's how we got those answers that quickly. And remember that our book tells us that all variables represent a positive number. Let's do number 48. Number 48. Number 48, this time we're going to be combining. So I'm looking at square root of 75. Y to the 5th over the square root of 3y. Now we can look at this separately. We can simplify this and figure out what we've got and see if anything cancels out. We can do that. We can ration the denominator when we go forward. But the most simplistic way is I know that 3 can go into 75 25 times, and I know y can go into y to the 4th. So I can really combine these, which is what our quotient rule says, that we end up with 75y to the 5th over 3y. Well, we know that simplifies. 3 goes into 75 25. And then y to the 5th, we subtract. That's a 1, so we end up with y to the 4th. Now we take the square root. We end up with 5y squared. And that is our answer. All right, I hope we're getting it. I hope we're getting it. All right, so that is it for that one. Let's talk about addition and subtracting radicals. So let's talk about adding and subtracting radicals. Again, I hope that you can rewind as you need to and go from there. Again, you want to keep up with your WebAssign. That is still in action, so don't think that's done. So addition and subtracting, adding and subtracting. It should be adding and subtracting, but it's addition and subtracting radicals. First of all, number 1, we're going to simplify first. So the first thing we're going to do is simplify. And after we simplify, we're going to treat it like combining like terms. Remember, COT stands for combine like terms, in terms of like radicals. We can do square root of 3 plus square root of 3, and that gives me 2 square roots of 3. But square root of 3 plus square root of 7 does not equal square root of 10. That is, again, remember what I wrote earlier, that is voodoo algebra. You took your wand out, thought you were Harry Potter, Hermione Granger, Luna Lovegood, Ron Weasley, Longbottom. You thought you were somebody and just waved your wand and said, Expelliarmus, I want you to be that. That doesn't work that way. It is not that. All right, so let's go to work and let's put this into action so we can see what exactly it is. Let's do number 54. Number 54. What number are we doing? 54. 54. We're on the next page of where we were before. So let's do number 54. 54 says 11 square root of 3 plus 2 square roots of 3. Well, aren't these like terms? This square root of 3 and this square root of 3, they have the same radical. So since they have the same radical, I can just combine them. So I got 11 of them here plus 2 over here, so that means I got 13 square roots of 3. And guess what? That's it. Let's do number 60. There was no simplifying there. Number 60 says square root of 20 plus square root of 125 minus square root of 80. Notice here, we have to simplify first. So in this one, we're going to have to simplify. Hopefully the next problem you'll be able to do on your own. But this problem, let's do it together. Well, I know that 20 is 4 times 5. So 20 breaks down to be 4 times 5. And I can square root 4. So this becomes 2 square roots of 5, because the square root of 4 is 2. All right, what about 125? Well, 125 is 25 times 5. So the 25, that becomes plus 5 square root of 5. Minus 80 is 16 times 5. And 18 becomes 16 square root of 16 is 4 square roots of 5. Notice now that they all have the like radical of square root of 5. So I can combine them. 2 plus 5 is 7 minus 4 gives us 3 square roots of 5. And that's it. All right, let's do number 68. Number 68. 68. Now I hope you try and push pause before you go forward. Let's try and make it a little harder. This time we're going to add variables in it. Let's take the square root of 80m minus the square root of 128m plus the square root of 288m. Okie dokie. So hopefully you got your list of squares, and we're going to break it down from there. Well, we just did 80. 80 is 16 times 5. So that ends up being 4 square root of 5, and the m stays on the inside because it couldn't come out because its index is already lower. Minus, now 128. How do we got to do 128? Well, 128 is 64 times 2. And I apologize, my phone rang. Please forgive. So 64 times 2. I didn't turn my ringer off like a smart person. Please forgive. So square root of 64 is 8. And then square root of 2m. Plus, let's do that 288. Well, 288 is 144 times 2. So square root of 144 is 12. Square root of what's left over, 2m. Notice that they're all not like here. Notice that they're not all like. The only two of them that are like are these two. So these are the only two that can be combined. You cannot combine this one because it's not like. This one is not like terms, so you cannot combine that. So all we're going to do is rewrite it just like having a y and an x, or a z and a q. They're not like terms, you can't combine them. I've got a negative 8 and a plus 12, so that gives me plus 4 square root of 2m. This is not 8 square root of 7m. That is voodoo algebra. Remember, if they're not like, we can't add them. All right, let's do one last problem. Let's do number 70. Let's do one more last problem, and then we're going to be done with this section. Number 70. Number 70 says, what does 70 say? 70 says, I'm going to do it with cube roots this time. Cube root of 250 minus 4 cube root of 5 plus cube root of 16, excuse me. So we got cube root of 250 minus 4 cube root of 5 plus cube root of 16. Well, the cube root of 250 is 125 times 2. So that becomes the cube root of 125 is 5 cube root of 2. This is the cube root of 125. Now, the 4 cube root of 5 is already simplified, so I can just rewrite this. Excuse me for having my pen in the way. 4 cube root of 5 plus, and then 16 is 8 times 2. So the cube root of 8 is just 2 cube root of 2. Again, we're going to combine like terms. Combine this one and combine that one. If I combine those, 5 plus 2 is 7, so I end up with 7 cube root of 2 minus 4 cube root of 5. And this is my answer. Alright, with that being said, we are done with this section. I'm going to stop the video here and go ahead and pick up again with a new video on 9.4. Actually, no, I think I'm going to go ahead and go straight forward and do 9.4 because 9.5 is kind of on the long side. So let's do this one first. Let's do 9.4 and then we'll stop. Let's go ahead and get 9.4 done and then we'll stop. 9.4. This time we're going to multiply and divide radical expressions. So we're going to multiply this time and divide radical expressions. And we're going to be on page, when we get done, we're going to be on page 774. So we're going to be on page 774. I want to make sure that you remember. I want you to remember our product rule. That says the nth root of a times the nth root of b is equal to the nth root of a times b. And our quotient rule that says the nth root of a divided by the nth root of b is equal to the nth root of a divided by b. Notice that the indexes have to be the same. You can't get busy and do a square root times a cube root. That doesn't work. The indexes have to be the same. There's one more rule that we want to talk about and we want to be reminded of, and that is the nth root, when we talked about the nth root a long time ago, of x to the nth power is equal to x if the nth root of x is a real number. So we want to be apprised of that. The nth root of x equals x if the nth root is a real number. And this is the nth power of the nth root. So if we take the nth power of an nth root, essentially we talk about they cancel each other out, because it ends up being just x, if the nth root of x originally is a real number. So let's do number 18. Let's get into it and put this into action and see how this comes out. Let's do number 18. Can I do some examples first? You know me, I like doing a lot of examples to make sure that we understand it. You know how I am. I like doing a lot of examples. Maybe in class I might cut it some because I know it's based on looking at you whether you understand it or not. But in this case, I can't see you and I'm by myself, so I got to do it on my own. I'm going through it over here. But that's okay, we can do it. Negative 3 square root of 11 times square root of 33. Well, there's multiple ways of doing this problem, and it's up to you to pick the way that works for you. But if we multiply this, we end up with a negative 3 times the square root of 363. Well, 363 is nothing but 121 times 3. Well, we know 121 is the square root of 11, so we end up with that negative 3 in the front times 11 with the square root of 3 left over on the inside. And then negative 3 times 11 is negative 33, square root of 3. Another way of approaching this is you could have done negative 3 square root of 11 times the square root of 33. You can look at square root of 33 as 3 times 11. So it ends up being negative 3 times 11 times the square root of 3 times square root of 11. Well, we end up with negative 3. Square root of 11 times square root of 11 is essentially square root of 11 squared, which we just talked about the nth power rule of the nth radical. We just talked about that, and that is just 11. So we end up with negative 3 times 11, and then don't forget this square root of 3 that was on the side going down. And we end up with negative 33 square root of 3. So those are two ways to approach this problem. It's up to you how you do it. Doesn't matter. That square root of 11 times square root of 11 is square root of 121, which is just 11. And then whenever I'm taking the square root times the same square root, then we ended up canceling the square root out, so to speak, and we end up with 11. All right, with that being said, let's try another one. We just did number 18, let's do number 20. Let's do number 20 this time. What does 20 say? What does 20 say? It says 2 times the cube root of 16 times the negative cube root of 4. So when we multiply the numbers on the outside first. The number on the outside here is a 1. Just like we normally do it with letters and numbers, we do our numbers on the outside of the radical first. So 2 times a negative 1 is just a negative 2. Cube root of, well, 16 times 4. Remember, we can put them together. That cube root of 16 times the cube root of 4 is nothing but the cube root of 16 times 4. Remember our product rule. That becomes the cube root of 64. Well, we know the cube root of 64 is 4, so negative 2 times 4 is a negative 8, and that's my answer. So just reminding us, remembering those rules that we have, our product rule, that allows us to multiply radicals. All right, let's try another one, and hopefully you're pausing as we go through to make sure you understand it, and you try it first before we try it. And this problem right here will be a great problem for you to do it. And of course, as I normally say, let's make it harder. 3 square root of 8x times 2 square root of 2x cubed y. So again, we're going to multiply, and because this parentheses there, it's just for typing and making it look pretty, but all we're doing is multiplying everything here. So I'm going to multiply the 3 times the 2. This is not distribution. I'm just going to multiply the 3 times the 2. Well, 3 times 2 is 6, and then I'm going to multiply underneath. The square root of 8 times 2 is 16. X times x cubed is x to the 4th, and then we have y going along for the ride. All right, so now let's take our square root. Well, square root of 16 is 4, so that becomes 6 times 4. And we blacked out again. We've got to make sure we keep that straight. Times the square, and then square root of x to the 4th is x squared, and then we're left with square root of y on the inside because this does not come out the radical. It is not, the index is already lower, so it's already simplified. 6 times 4 is 24, so we end up with 24x squared, square root of y. 6 times 4x squared, we end up with 6 times 4 is 24, so we end up with 24x squared, square root of y. All right, let's do number 30. I hope you're pausing and trying it on your own. Let's take negative 3. Well, negative square root of 3, excuse me. Negative square root of 3 times square root of 7 minus square root of 15. Notice we can't combine these two, but we can distribute. So I'm going to distribute. And you know me, I like drawing arrows because some of us don't. If we remember to multiply both of them, we only multiply one. So a negative square root of 3 times the square root of 7 is a negative square root of 21. A negative square root of 3 times negative square root of 15 is a positive square root of 45. Now we simplify. Can you simplify 21? Well, 21 is 3 times 7. There's no perfect square for 3 and 7, so that doesn't work. But square root of 45 is 4 times 9. Oh, no. No, it's not. It's 9 times 5. I'm having a moment. 9 times 5. So we can simplify that. So we end up with negative square root of 21 plus 3 square roots of 5. I'm getting nervous for some reason, so I need to relax and calm down. Sorry about that. Square root of 45 is 9 times 5. I do apologize about that. I need to relax and calm down and chill. Whew. Okay. All right, let's get back to it. So that was number 30. Let's try number 36. You know me, I like doing a bunch of examples because I don't want you to say I didn't have any example of how to do this problem. Let's take 2 square roots of 3 plus 1 times square root of 3 minus 1. Well, if I made these variables, wouldn't this look like a FOIL problem or a distribute problem? Same thing. We can do it here. Oh dear, I pushed the button. Sorry. There we go. So doesn't it look like a distribute problem? So or FOIL, let's go to it. 2 square root of 3 times square root of 3 is just 2 times square root of 3 squared. Well, let's write it out so that way we have it. Then the outside we have a negative 2 square roots of 3. Inside plus square root of 3. And last minus 1. Remember we talked about it. If you take square root of 3 times square root of 3, that's just 9. Square root of 9 is 3, so this is just 2 times 3. Which is 6, yes, minus 2 square roots of 3. Plus square root of 3 minus 1. You really can just go straight to 3 from here. Don't even have to do the mindset. If you multiply a square root times the same square root, it's just that number because when you square it, it cancels the square root out, so to speak. So here we go. A negative 2 plus 1 ends up being, well, 6 minus 1 is 5. And negative 2 plus 1 is a minus square root of 3. And guess what? I'm done. That's it. That's it. Don't make this harder as it has to be. It is what it is. Now, if you're having a difficult time, that's fine. Let's talk. Let's talk about it. Rewind it. Replay it. Do whatever you need to do. Do what you need to do. For those of you who are not understanding what I did this times this. Then I did this times this. Then I did this times this. And then this times that. So just for those of you who might not remember how to FOIL or how to distribute, that's what I did. Let's do number 40. And hopefully you're trying it at home again to make sure you've got it before we see it together. Let's take 4 cube root of 9 minus 3 cube root of 3 times 4 cube root of 3 plus 2 cube root of 6. So let's take 4 cube root of 9 minus 3 cube root of 3 times 4 cube root of 3 plus 2 cube root of 6. So let's multiply, let's get this together and multiply it out. Let's see what we get. If we take 4 times, we're going to do our FOIL, and I'm not drawing arrows. I think you know how we did it before. If I take 4 cube root of 9, no, let's go on and draw arrows so we don't have no mistakes. I'm going to do a FOIL this time. So at first, so I end up with 16, and 9 times 3 is 27, so I get the cube root of 27. First, then outer. So we end up with plus 8 cube root of 9 times 6 is 54. Then we have inner. We've got minus 12 cube root of 9. And then last. And then we have minus 6, and I'm running out of room. Minus 6 cube root of 18. So I multiply my numbers first, and then my radicals, I multiplied and combined them because they have the same index. Now let's simplify. Well, cube root of 27 is just 3. So that ends up being 48. 16 times 3 is 48. Plus 8. Well, 54 is nothing but 27 times 2. Cube root of 27 is 3. Sometimes in by 3. And then we have the cube root of 2 left over. Minus 12. The cube root of 9 stays what it is because there's no simplifying. There is no cube root of 9, and 2 doesn't go into 9, so that doesn't help. And then minus 6. The cube root of 18, there's no simplifying that either. 8 doesn't go into it, and then 27 doesn't go into it. So we're done with that. Now let's do what we've got. 8 times 3 is 24, so my answer ends up being 48 plus 24 cube root of 2 minus 12 cube root of 9 minus 6 cube root of 18. And that's number 40. Is there any questions over that so far? Any questions over that so far? All right, let's move on then to number 44. Let's try number 44. If you have questions, again, rewind, replay, see if you can get it. And if not, by all means, look on Khan Academy, look on other videos on YouTube, and see if you can figure it out from there. And if not, again, come to virtual office hours and let's talk about it. Let's figure this out, or virtual classroom, and go over our homework problems today. All right, let's do number 44. Let's take square root of 11 squared, and we went over this rule just a little bit ago, talking about the nth power of an nth radical. They essentially cancel each other out, so we're left with just 11. That's it. Let's try number 50. Number 50. Ms. V, how does that work? I want to go back over this. Isn't square root of 11 in rational form 11 to the 1/2? Squared, don't we multiply, so we end up with 11 times 1/2 times 2? Isn't that just 1? So that's another reason why that works also. Let's do number 50. Negative 3 cube root of 10y cubed. And we're raising it to the third power. Well, remember our exponent rules. When we take the power over a product, we got to raise both things to the third power. So we're going to have negative 3 to the third. Yes. And then times the cube root of 10y cubed to the third. What happens with these powers? They end up canceling each other out, as we saw over here. So we're left with a negative 27 times 10y cubed. I didn't even have to simplify it out first, because this cube canceled that. And then I'm left with negative 270 y to the third. And that's it. All right, good. Let's try another one. Let's do number 54. This is the last one of this portion here. And that is square root of 5x minus square root of 3. Now, if you don't know your the perfect square trinomial formula for this, or the squaring a two-term expression, we'll learn that actually in the subsequent chapter. I think it's chapter 10. We will actually have to know that formula. But for right now, we're going to go ahead. We can rewrite this and just write this as square root of 5x minus square root of 3 times square root of 5x minus square root of 3. And then FOIL it out. Again, drawing my arrows. I'm going to distribute this time because it makes it a whole lot easier in terms of drawing. I end up with square root of 5x times square root of 5x. We talked about this. That's just 5x. Square root of 5x times negative square root of 3. That's negative square root of 15x. Going back the other way. Now we're going square root of 3. Doing those two now. Let's do square root of 3. There's a negative square root of 15x. And negative square root of 3 times negative square root of 3, well, that becomes a positive just 3. We talked about that. That's square root of 3 times square root of 3 is just 3. All right, now we combine like terms. These are like, so end up with 5x. We usually put our number first, which is plus 3, our constant term, and then our radical. And we've got two of those, so minus 2 square root of 15x. And guess what? That's it. That's it. All right, I almost need to pause it, but I'm not going to. We're going to keep going. You might want to pause it, and you might say, Ms. B, I need a break now. And that's fine. Go ahead. You might need to pause it, but we haven't really been on the video that long, so it's not that bad, but we can handle it. Let's go ahead and go to, let's go ahead and go to talking about what if there is a radical in the denominator. So if I do all my math and I end up with a radical in the denominator, we can do what we call rationalize the denominator. It essentially is multiplying the denominator by a factor of a radical with the same index. That simplifies or cancels out my radical. So it's multiplying the denominator by a factor of a radical with the same index that somewhat simplifies or cancels out my radical. And that's what it is. Let's put this into action so we can look at that idea. Oh, remember, sidebar, whatever you do to the bottom, in order for us to maintain that inequality, we must also multiply to the top. And of course, we know the proper names is denominator and numerator. But that's just a way to think about it. Whatever you do to the bottom, you got to also do to the top. Just remember that. Don't get busy and just multiply the bottom. You got to multiply the top also. Let's do number 58 and see what we're talking about. End up with the square root of 8 over 7. Well, if I notice that 8 and 7 don't really go into each other, but if I use my quotient rule, I can rewrite this as square root of 8 over square root of 7. That square root of 7 is not going to get out the denominator because that square root of 7 is prime. So there is no square root of 7. But I want to think about what can I multiply square root of 7 by that's going to get rid of my radical. But if I multiply this by another square root of 7, then doesn't this bottom now become just 7? And then remembering that whatever I do to the bottom, I have to do to the top. So I end up with square root of 56 on the top. So we're multiplying top and bottom by square root of 7. Then I'm going to simplify my 56. Well, 56 is, let's see, 4 times 14. So this becomes 2 square root of 14 over 7. Now that 7 cannot divide into the square root. You cannot do 7 square root of 14 over 7 is equal to square root of 2. That is voodoo algebra. You cannot divide numbers that are under the radical and numbers that are not under the radical. They both have to be under the radical in order for you to combine them. So you cannot combine them if they're not both under the radical. These are not both under the radical, so they cannot be combined. That is voodoo algebra. Let's try another problem. Let's do 64. And hopefully you'll try this one on your own before we do it together. But let's see how you come out. 64. Pause your video and try it. Well, maybe not yet. 2 over the cube root of a. 2 over the cube root of a. Oops, can't see it. All right, there we go. 2 over the cube root of a. What do I have to multiply to top and bottom to be able to get my cube root to go away? Well, I see an a. When I get done, I want a to be a cubed. That's what I want. So what do I have to do in order for my radical to go away? I need this cubed. So what do I have to multiply a by to make a cubed? Yes, you guessed it. I got to multiply it by cube root of a squared. If I do that to the bottom, again, I have to do that to the what? Top. So I end up with 2 cube root of a squared over, and I just want to show it in step, that's a cubed. Well, the cube root of a cubed, we know those cancel out. So left with 2 cube root of a squared over a, and then I'm done. So notice that we're rationalizing the denominator, getting the radical out the denominator. All right, let's try and make it harder. Let's do number 72. 72. Let's take the cube root of 15 m to the 4th over the cube root of 12 m cubed. Sometimes simplifying it makes it easier, and sometimes it doesn't. It depends on the situation. You can approach this right here. You can make this all one radical and get rid of the m off the bottom and deal with that. Or you can do multiple things. When I approach this problem, I'm not going to try to multiply and do all kind of interesting stuff, but I want to look at 12. What do I have to multiply by 12 to make it a 12 cube? Because I want to simplify it. Now, when you're dealing with bigger numbers, sometimes it makes it a little bit more, I guess, verbose, or so to speak, a little bit messy when you deal with big numbers. So I really can simplify this and put this all together and say 15m to the 4th over 12m to the 3rd. If I do that, then I find out that I can simplify by dividing by 3, and then put the cube root of 5m over just 3. No, I don't. That's 4. Excuse me. Dividing by 3, that's 4. Apologize. That's why I wanted to write it in pencil, because I start making mistakes. Apologize. So if I take the cube root of 5m over 4, if I break that up again, then I end up with the cube root of 5m over the cube root of 4. I want to make 4 into a perfect cube. What can I do to 4? To make that, I want 4 to be something cubed. Well, if I times this by 2, don't I get 8, which is 2 cubed? So that's exactly what I'm going to do. I'm going to multiply this by the cube root of 2. You have to think about what you can multiply, that I'm going to get something cubed. So if I multiply that 4, then I end up with the cube root of 10m over the cube root of 8. And noticing by me making it smaller numbers, it's easier to identify. So by making it smaller numbers, I'm able to identify it easier. And so this gives us the answer of the cube root of 10m over 2. And that's my answer. Are there any questions over that? Any questions? Any questions? Oh, I can't even answer it. Not right now, but I can answer it later. All right, so rewind again if you need to help you understand that problem, etc. Let's do number 78. Let's make it a little harder this time. You know I love making it harder. Let's take 13 over 32 n cubed, and we're doing the square root of 32 n cubed. Square root of 32 n cubed. So I'm going to simplify it first, so I don't have to worry about using big numbers. Just like we did in the previous problem, I'm going to simplify it first, so I don't have to worry about big numbers. And again, I will hope you would try it first before you did it with me. But again, I'm going straight to it. 32 is 16 times 2. So I can rewrite this as, and don't forget the index here is a 2, just to remind you. I end up with 13 over 4 on the outside, and let's do our letters, and then the cube root of 2, then the square root of 2 on the inside. Excuse me, I'm getting happy. And then 2 goes into 3 once, with 1 left over for my variable. That is what we end up with. So what do I have to multiply by to get rid of that radical? So by me simplifying it down here, now it's not so bad when I multiply. So I'm just going to multiply by square root of 2n. And if I multiply the bottom, I have to multiply the top by square root of 2n. And so I end up with 13 root 2n over 4n times 2n, which gives us 13 root 2n over 8n squared. And that is my answer. Okie dokie. Let's try one more problem. Let's do number 82 this time. I'm going to put it up here a little bit so it gives me a little bit more room. 82. Let's take the cube root of 7 over 16. 7 over 16. Well, we know that's the same as writing the cube root of 7 over the cube root of 16. And of course, you can simplify this again. Actually, I think I'm going to do this without simplifying, because when it's just numbers, it makes it kind of just as easy to not do it. We want to know, what do I need to multiply 16 by so that it can be something cubed? But if I multiply this by the cube root of 4, and I do it on top and bottom, then I'll see that I'll end up with the cube root of 28 over the cube root of 64. Well, is it 64 a perfect cube? It is. So I end up with the cube root of 28 over 4. And that's my answer. Now I'm going to do this alternatively from here a second way. Simplifying first. I got cube root of 7 over the cube root of 16, showing you that it works both ways. Cube root of 16 is 8 times 2. So I'm left with the cube root of 7 over 2 cube root of 2. Again, what do I have to multiply by 2 to make it a perfect cube? I'm going to multiply by cube root of 4, just like we did before. And I end up with the cube root of 7, 28 actually, over the cube root. No, come on, talk to me, Celeste. Oh, 2 times the cube root of 8. Well, what is the cube root of 8? We know the cube root of 8 is just 2. So that becomes 2 times 2 over the cube root of 28, which gives us this answer right here. So I was able to do this 2 different ways. So you pick the way that works for you. As I normally say, pick the method, the way that works for you. Sorry, I don't know what's wrong with me. I got nervous all of a sudden. What is wrong with me? So let's move forward. And of course, I didn't make sure that there was no stapler in the scratch paper before I started like a smart person. So I'm wasting precious time. So I can do this problem, but that's okay. We can make it work. Let's go to number. We just did 82. Now let's talk about a couple more situations before we shut 9.4 down. We said 9.5 was long. My goodness, 9.4 is turning out to be very lengthy. But that's okay, we can handle it. Let's talk about what if the denominator is a sum or difference. In other words, I'm dealing with 2 terms. Then you have to multiply by what we call the conjugate. So to rationalize the denominator, you have to multiply both the numerator and the denominator by the conjugate. Well, what is the conjugate? The conjugate of a plus b is a minus b. So it's essentially what you have to multiply. It's essentially the opposites with just the variables not changed. You change them plus to minus, that is the conjugate. That way, if I multiply a plus b times a minus b, don't we get a squared minus b squared? What happens? If I have a radical here and a radical here, and I multiply by the conjugate, doesn't that make my radical go away? My radical ends up going away. So that makes my life a whole lot easier. So that's why we multiply by the conjugate. It negates the square root, or cancels the square root. Let's do number 92. So we're going to multiply by the conjugate. Again, multiplying by the conjugate. And we'll use this again when we talk about complex numbers. We'll talk about that idea. Let's take the square root of 3 over the square root of 3 minus 2. Now, a lot of times when we write this in standard form, we usually put the radical on the right, but we can handle it if the radical is on the left. It does not matter for the problem. We want to rationalize our denominator. So to do that, we're going to multiply the top and bottom by that conjugate. The conjugate is going to just be the same thing, but instead we're going to add this time. Now remember, on the top you're going to have to distribute, so be careful with that. So we end up with square root of 3 times square root of 3, we know is just 3, plus 2 square roots of 3 up top over this square root of 3 times square root of 3 is 3. And then we know it's a squared minus b squared, so minus 4. So and we end up with 3 plus 2 square roots of 3 over a negative 1, which is just negative 3 minus 2 square roots of 3. What did you do, Miss B? I divided both of them by that negative 1. I split them up. And so we end up with an answer like that. Is there any question? So you do need to simplify it. All right, why don't you try this time? Well, let's make it a little harder. Maybe you try, pause it, try it, and see how you come out. Let's take square root of number 96. Let's take square root of 3 plus square root of 2 times square root of 3 minus square root of 2. Again, same type of bottom, but this time we have 2 radicals. First step we need to do is we need to multiply top and bottom by the conjugate. So we're going to multiply square root of 3 plus square root of 2 and square root of 3 plus square root of 2. Remember, whatever you multiply on the bottom, you got to multiply on the top. We're multiplying by the conjugate. So let's go straight across. Let's multiply. We're going to FOIL it. So first, and we end up with 3. Then outer, so we end up with plus square root of 6. Inner, we end up with plus square root of 6. And last, we end up with 2. On the bottom is a squared minus b squared, so we end up with 3 minus 2. Because when I square root of 3, I just get 3. And if I square root of 2, I just get 2. So simplified, 2 plus 3 is 5, plus 2 square roots of 6 over 1, which is just 5 plus 2 square root of 6. You do want to break it up and simplify, just like we did before. So if you end up with a different denominator, you do want to separate those and simplify them. All right, for example, if you had something like, and again, I'm sorry about the screen going out. Let's say you had something like 3 plus square root of 4, square root of 5 over 7. Then you would want to write 3 over 7 plus square root of 5 over 7. And I'm thinking down the road. Technically, I'll take this on the test, but this would be a little bit more proper to write. But I would take this on the test. But if it can simplify out, separating it will help us simplify it much better. Okay, let's talk about one more idea before we finish 9.4. Let's talk about one more idea before we finish 9.4. And that is if they want us, if they ask to rationalize the numerator. Well, it's the same idea as rationalizing the denominator. So it's the same idea as rationalizing the denominator. So if we rationalize the numerator, it's the same as rationalizing the denominator. Let's look at number 102. So we're looking at number 102. Number 102 says square root of x minus square root of y over square root of x plus square root of y. So we take square root of x minus square root of y over square root of x plus square root of y. They want me to rationalize the numerator this time. So we're going to multiply by the conjugate, the same way we know to do. So we're going to take this and times it by square root of x plus square root of y. Just doing as the directions told us. Normally when we want to simplify a radical, we rationalize the denominator, but this time they specifically asked us to rationalize the numerator. So we get conjugate, so we end up with difference of two squares, that's x minus y, and then on the bottom we FOIL it out. So we end up with, for square root of x, so we end up with x, then we end up with plus square root of xy, plus square root of y at x, and then plus y. Maybe that's a little confusing with my lines, but they are pretty much multiplying, FOILing it out. So we end up with x minus y over x plus y. And then these two are the same. Yx is nothing but xy. So that's plus 2 square root of xy. And that is my answer. All right, thank you so much. We finished section 9.4. Thank you so much. You should be able to do your WebAssign homework. You should be doing most of your WebAssign homework now. Thank you so much, and we will resume 9.5 on the next video. Thank you.